binary heaps. On Tuesday, we started talking about binary heaps. In fact, you surprised me. I shouldn't say I surprised myself. You surprised me because we got way further than I thought we would have in that one lecture. And we got as far as working out, actually inserting numbers into a specific binary heap. So we covered what a heap is, we covered why it works fast, we covered how you could use it to implement a priority queue, and we covered how to insert into the binary heap using an example. So a lot of that went by real fast. I'm going to just write up a recap in terms of the procedure, because we didn't document the procedure, but if you were following, I think you could have documented it yourself based on the example that you saw. And then we'll look at how you delete. I sort of a 10,000-foot view. I gave you that on Tuesday, but today we'll actually look at the specific procedure and then do an example. And then we're going to move into the next section of the topic set that we have to cover, which is dictionaries and binary search trees. But before I do that, and this is coming up on your tutorial next week, I'm going to talk a little bit about how you would go about dealing with some of the. Remember, I left you with a question last Tuesday. I said, how do you know where to insert? Remember I said that? Because you have to find the leftmost available location at the leaf level. How do you know where that is? So we're going to talk a little bit about the efficacy of your implementation. All right, so quick recap. Remember that to insert, so to insert into a binary heap, so we're going to insert new element at the leftmost available position in the current leaf level. And of course, if you have none in the current leaf level, you have to start a new level if the current level is full. And then the second part of that is to repeatedly swap with the parent until what's called the heap ordering property, which is property 1. Is restored. Okay, so that's what we were doing in class on Tuesday with those numbers. That's the procedure we were carrying out. So to delete, what you want to do is and bear in mind, you're not allowed to delete any element. We're only talking about deleting the smallest element because it's remember, it's implementation of priority queue. When you remove an element from the priority queue, the only one you're really talking about removing is the one at the highest priority element. So it's not an arbitrary element you're trying to delete. It is a very specific one. So we're talking about deleting the min. And of course, that is really the highest priority element. If you had a priority system that made big numbers mean higher priority, then of course you'd be deleting the max. But to delete the min, we're gonna execute 3 stages of steps really. One is, the first step is copy up the rightmost leaf into the roots. And then structurally remove the rightmost leaf. And then repeatedly, let's call it push down the root value exchanging with the smaller of the 2 children at each step until the heap ordering property is restored. Okay, let me sketch that for you. Well, I'll illustrate it with an example rather than sketch an abstract tree. So, let's say delete the minimum element from the following heap. And I think I'll try and reconstruct a tree that looks similar to what we had constructed on Tuesday. I think maybe there's a 1 in there. I think there might have been I don't know, 4. In fact, it doesn't really matter. Let me construct a fresh example. There's an example of a heap, and the instruction is to try and delete the minimum, actually delete the minimum element from it. And so if you follow these rules, the first step is, so remember, the heap ordering property just says that at every level, the value stored at a node is smaller than its children, because we're dealing with minimizing heaps. There's no constraint about left to right ordering. The second property of the heap had to do with the structure of the heap. The shape of the heap is always such that the leaf level is filled from left to right, and you don't ever have holes in that space. So if leaves are missing, they'll always be to the right side. And as new items are inserted, they must proceed to fill in the rest of that leaf level before you can start the next level. So likewise, you can imagine that when you're deleting an element, you'd have to delete from the right of the leaf level. And the one to go first would have to be the rightmost leaf. In other words, structurally, what you want to do is remove this node because it's the rightmost at the leaf level. The problem is that what you're asked to actually delete is this node, which is the one with the 1, because that's the one with the highest priority. So how do we fix this? According to this, what you say, okay, copy, take data from this node. This is the node you're going to actually eliminate, but take the data from there and copy it into one. And that way you're not going to touch a structure apart from this easy one to reach. So we're going to copy that 70 into here. Step 1. And then step 2 is chop this out. So now that node is gone. Okay? If this were a linked structure, how do I delete a node? As in, get rid of it. What does this encode? What does this actually translate to? What would I be doing there? I'll be setting the left, whatever the representation is for my tree. However I store my left subtree, it might be, for example, an item in a list. I'd be setting that left to the empty tree. That's how I would get rid of it. Make sense? So that's what I mean by get rid of it. You're actually going to collaborate with empty tree. Okay, once that's done, then you're going to move into phase 3, which is to repeatedly swap the root value and pushing it down. This process sometimes has its own name. It's actually sometimes called fix heap. I'll sometimes refer to it as fix heap. The textbook that's prescribed refers to it as fix heap. And the reason why it gets its own name is because it gets a use in another context as well. It's not just for deleting, but you'll see in the tutorial question that you can use it for constructing heaps from an array. All right. Now, so let's focus on what fix heap would do. You're going to compare this 70 with the 5 and the 3. It's obviously out of place relative to both. And so what you're essentially doing at each stage is looking at the two children and taking the smaller of the two and swapping with the current node. So you're going to swap the 70 with the 3 in this case. Make sense? So then that's going to bring the 3 up, the 5 on the left, the 70 on the right, and of course the rest of over here being changed up. In this case, I only needed to move one step, but in general, of course, you'd have to keep doing that until you potentially got to the leaf level. In fact, it's quite likely, since the value that you just cut came from the leaf level, it's quite likely that you may have to push it quite far down that heap. But no guarantees, because remember, there's no relative ordering between left and right. So you could end up pulling a relatively small value from the right side of the tree. When you put it at the top and you start pushing it down, it ends up going to the left side, and it doesn't go very far because you have a whole heap of big values on the left side. So it doesn't guarantee that you always go back all the way down to the leaf level, but you wouldn't be surprised if it did because the original value came from the leaf level in the first place. Either way, even in the worst case, if you end up traveling all the way down to the leaf level before you stop, what is the time complexity of that? Log n. Yeah. Not n over 2. Log n. Auto log n because the height is proportional to log n. We proved that on Tuesday. So your time for delete min say to log n because it's proportional to the height. Okay, any questions on that? All right, so now we'll come to the fun part. Yeah, where you're actually going to learn something. Well, maybe you learned something this while ago, but it may feel a little abstract. I'm going to try and teach you something where you feel like you could code. So now, let's try and answer the question, how do I know when I'm ready to insert? Let me ask a question first. If I have to insert into this heap, if I have to insert the value 2, where do I stick that node 2 in the first place? Left of the 70. Very good. Okay. Now the question is, how do I find that location? Remember how linked structures work. When I'm talking about a tree like this, what do I actually see when I see this tree? Do I see all these numbers here? I only see the node 3, the node with 3 in it, and I see a left subtree and a right subtree. That's it. And I see those subtrees, I don't see what's in them. So I don't see the 5 and I don't see the 70, right? I only see that there are references to somewhere that when I go there and look, I will see the 5 and the 70. So that's all I'm seeing. Now I'm supposed to somehow know when I have to insert this 2 into this tree, that in this situation, to find the link, because to put it at the left of the 70, I have to actually find the node containing 70 and then set its left subtree to be a new node containing 2, don't it? That's what it means to insert a node there. Which would mean that when I'm traversing this tree, I must somehow know I need to go right. How do I know that? Check the what? The length of? You mean the size? Because trees don't have lengths. How will I know how many nodes are in there? You want me to count them every time?
Oh, sir, no.
How will I, sorry? Subtract what from what? No, okay, one idea is if I knew how many nodes were on the left side and on the right side, I would know whether I should go right or left. That's not a bad idea. And in fact, if I could magically know that, then yes, I could do that. But I don't know how many nodes are in my subtree. I would have to go and crawl the tree to find out. And I don't want, that's the whole point. I don't want to explore the whole tree just to, all of this lovely stuff is predicated on the fact, or the presumption, that, for example, when I'm ready to insert, remember, I didn't even account for the time it took to stick a new node here. When we reasoned about the length of time it takes to do an insertion, all we did was say, oh, once you stick it here, what was the maximum number of levels it would need to go up? I mean, that's how we concluded that it was order log n. Now, if the time it's going to take it to stick it here is going to be order n, well, you're just killing the performance, right? So the trick here, the question is, how do I locate where it belongs cheaply? I can't spend too much, I can't spend more than log n time or effort finding where it must go. And right now you're faced with the decision, if I'm starting here, I need to decide whether I must go left or right to find a node that's supposed to own the new node, the new inserted node. Any ideas? Any more ideas? It's kind of mysterious, isn't it? Sorry? Okay, I mean, right. So you could get into trying to annotate the data with extra data about how many children the node might have, and so on. And actually, there is a way to make that work, where you could keep the size of the subtree beneath a node, right? But I would require extra data. So there is a way to do it that way. Right. That's not the way I'm going to show you.
Surely.
There's a more efficient way to do that, But that is a handy thing to keep in mind when you have trees that are less structured, less well behaved than heap. All right. Let me illustrate to you an observation about these trees. Here's the magic that's going to happen. If you know how many nodes are in the tree, I know this is an easier thing to keep track of than the number of nodes in your subtree. I just need to know the total number of nodes in the heap. All right, I don't need to know the number of nodes at every level.
Because I haven't slept all night.
So
stay awake.
Observe the following. Actually, let me leave it on this one.
Okay. coming to school shortly.
I'm going to label these nodes
Waiting on the analysis.
from top to bottom, left to right.
I'm extremely
All right.
excited.
So here we go. This is node number 1. This is node number 2. This is node number 3, 4, and 5.
Okay,
So if I wanted to try and insert a new node, it needs to go into what I would call position 6. Yes?
I'm extremely exhausted.
Cypher, your mic is on.
I haven't slept any at all.
Thank you.
Okay.
Cypher, your mic is on. It's going to be in the recording. Could you turn it off, please?
You can mute them, sir.
Thank you.
All right. Somebody else's microphone. My laptop mic should be off. That's off, right? Yeah. Yeah, that's how it should be. That's fine. Okay. So watch the following. Watch what happens. I'm going to write the numbers here, these indexes, in binary. All right, so what's this? In binary. 1, 0. And what's this one? 1, 1. And this one is 1, 0, 0. And this one is 1, 0, 1. And so 6 would have been position 6, which would have been for this guy. In binary, it would have been 1, 1, 0. Okay. So here's the trick. The first one is for the root. And then as you go from left to right, a 0 means go left and a 1 means go right. All right, so let's watch that work. So if I want to find, if I want to find position 5, what was that? Witchcraft? If I want to find position 5, 1, 0, 1, that means go left and then right. If I want to find position 6, that means go right and then go left. Isn't that neat? Do it again. All right. Let's. I could have said new element. So let's illustrate that. So I'm gonna draw a heap with more nodes in it. Just so you can see. All right. So how many nodes do I have here? Well, that level had 8, so that must be node number 15. 16, 17, 18, 19, 20, 21, 22. So the next position to insert would have been position 23, yes? '23 in binary is what? All right, so that's a 16, no 8, but then a 7, right? Right? Okay. That's the binary for 23? Yes? Everybody stick with me. Stay with me here. That's the binary for 23. So remember, I'm at the top here. I don't see all these nodes. I just see left and right. So what do I do now? I look at this and I go, oh, 0 says go left. So from here I'd go to this. So I would say go left. So I'd go like this. The next bit is a 1, which says go right. So then I'm going to go this way. The next bit says right 1, so go right. And the last bit is a 1, so it means stick it on the right of that note. See it? Right. So the time to do that is what? I don't have any decisions to make, right? I just follow the instructions of the bits. And so the length of time it's going to take me to get to where I'm supposed to stick that new node is going to be the length of this bit string, or if you wish, the height of this tree. So it'll take me log n time to go down, stick the new node in with the new value, and then restore the heap ordering property by swapping as necessary. So possibly another log n time to go up. Yes? Okay. Any questions? Yes? How what? Don't worry about that one. I'm gonna illustrate a better way to do this, but it requires a little bit more infrastructure change, and then you'll begin to see when I do that. You may not. I mean, okay. It's kind of like, you know, when you have a proof by induction that works, you say, how you know it's right? Well, the induction tells you it's right, but how did you come up with the formula in the first place? You don't have a good answer for that. All right? Yes, question. What do I mean by 1 base as opposed to 0 base? A 0 base index would start from 0, 1 base starts from 1. So, in other words, if you start counting from 0, you're going to get this wrong, because you're going to get a different bit pattern which sends you somewhere else. So you have to regard the root as number 1, not number 0, not element 0. That's what I mean by 1 base. What? Yes, question? Well, you know what to say about magic. Magic is just technology that's so advanced you don't understand it. So at this point, it's kind of relative. If you're not understanding it, it's still magic to you. If you fully understand what's going on, then it's just high tech. Yeah. All right. Let's take a look at how we can improve this even more. So one of the things about heaps, binary heaps, is that those nodes are really well behaved. We only put them in left to right order. And based on what you just saw, there's this really neat mapping between the indexes of those nodes. And if you imagine I were to pack this into an array, then in fact this would correspond to putting this root element at index 1, and then this left child at index 2, the right child at index 3, and so on. So in fact, what's nice about this is that if I pack it into an array, the array is actually really well packed. The first, if this is n nodes, I'll have the first n elements all full of data. And then the rest of it, you know, if I have to allocate enough space ahead of time, but the rest of that array is just future space to hold space to hold the future nodes, right? Now, if that's true, then you realize that to insert, I actually don't need to track that tree down. I don't need to go left, right, down. I know exactly which index it belongs to. I can just drop the new value in there. So I don't spend the login time going down the tree. I only spend the login time coming back up, possibly because I might have to restore the heap order. So I can embed the heap in an array using the same mapping that we just discussed. Use these indexes, embed it in an array, and then the actual initial insertion now is done in order one time, and then the restoring heap order property may take still log n time because you might have to swap. When you do that, all you have to bear in mind what you now need to bear in mind is that if I now point at an index I, which then corresponds to some node, what I'm going to need, let's say that this was index I, what I need to understand is when I want the left child, how do I find it? When I want the right child, how do I find that? Where in the array is the left and right child of a given index I located? Anybody can tell me based on what you saw here? Okay, be more specific. Left is even, but there are lots of even numbers.
Wait, sir.
Yes, yes.
Wouldn't the left node be 0?
The left node
Would not be 0, and the right node would be 1?
No. All right, so okay, you're on the right track, but obviously not every left node can be 0 because each node has a unique address. The suggestion was, would the left node be 0 and the right node be 1? The left node would be the equivalent of putting a 0 on the end of the binary for I. That make sense? Because what about the value for I is, you think of that as a bit string having gotten you to that path. Now, putting a 0 on the end of that would take it to the left, and putting a 1 on that would take it to the right. What does it mean to put a 0 on the end of a bit string? What are you doing numerically? Yeah, you left shift, and arithmetically, what are you doing? Multiplying by 2, doubling it. So if your index is I, the left child is going to be at 2i. And therefore, what's the right child going to be? 2i plus 1. And with that, you have a complete mapping. So I can embed a heap in an array. It's going to be compact. And all you need to know, if the its left child at position 2i, and it has its right child at position 2i plus 1. And of course, naturally, if I give you, where's its parent? If the node is at I, where's its parent? Ceiling or the floor. That's, you see, that's a mathematician. When we think in computer science, you just think integer divide, right? Which is going to give you the floor. You want the floor because you want a 2i plus 1 over 2 gives you back I. And if you took the ceiling, you got an I plus 1. So you want the floor. All right. Great. So we just covered. So now if you have to implement a heap in real life, yes, this is how you imagine it as a tree, but reach for the array embedding implementation, okay? Don't go off building binary trees with lots of links.
Excuse me, sir.
The slowness. Yes, question?
We can no longer see the board.
Help. I can't see the board anymore. I think it probably bounced. I think they want to see the bottom on there. Is that, well, all right. Okay, so that's it for priority queues and binary heaps. Binary heaps is your better way to implement your priority queue. So I'm going to move on to the next ADT that we need to cover. And in fact, I'm going to segue from the binary heap with the following question to you. Suppose that, well, okay, I have to motivate this properly. So suppose that I wanted to search for an element. So I've stuck things into my heap. If I wanted to find out if the value 4 is in this heap, how would I do it? Is there any efficient way to do this? Like when I compare with the root, that this one over here, this left heap over here. If I compare the root, I'm seeing at 3, but I'm looking for 4. So it's not at the roots. Can I decide whether I must go left or right to search for that 4? How? But what will it tell you? What will it tell you? So if I check for here and 5, okay, there are a couple of things I can learn. When I look over here and I see a 5 on the left side and it's not equal to 4, what does that tell me? Okay, I don't need to go any further because all numbers deeper are bigger. Fine. How about, does it eliminate me checking on the right side though? No. All right, so in other words, suppose I'm checking for the value 100, what happens? When I look at 3, I don't see the 100, which way do I go? Left or right? What? Left or right? I need to check both sides. There's no information I get when I go to the left and say, oh yeah, there's no 100 over here. It tells me nothing about whether the 100 could be on the right side. And that is true at every level. So a heap is terrible for searching. You never try and search a binary heap. It's just as bad as searching a linked list or just searching an unordered array. You can spend all the n time doing it. Okay? So, you all know what a dictionary is? So a dictionary is exactly that kind of structure. You want to be able to store stuff in it and then look it up later. So of course you have, we have our make dictionary. It's just a construct an empty dictionary. But we're going to want to do an insert. Sometimes we call it put. And when we're inserting, we're going to want to store an association. So it's not usually just a one thing. You're trying to store, typically you'd store a key and a value. And what we want to do there is associate the key K with our value V in D, in the dictionary D. And of course, it's no use if all you can do is store things if you can't look them up. So we're going to want to do a lookup, or sometimes called a get. So sometimes insert is called a put, and sometimes the lookup is referred to as a get. And what we want to do is return the value associated with K in the dictionary. Good. So having had that little spiel before I started talking about dictionaries, if I propose to you, let's use a binary heap to back our dictionary, what would you say to that? No, right. No. Okay. Right. Straight. No. Bad idea. So let's examine what we could do in order to support this efficiently, or we hope. So just like what we did before when we examined a priority queue, let's ask ourselves, what technologies do we already have at our disposal, and let's examine what the time complexities would be if we were to do it that way. And then we're going to question whether we can do any better. So what's your favorite go-to data structure when, yeah, your linked list, right? No? Sorry? A list? Yeah, okay, well, so you're brought up on Python, so you think you have lists as in array kind of thing. But these are dynamic structures. And a classic array like in C or Java is not good for this because you would have a limited capacity. And then inserting, when you buck up on the edge of it, you have a problem. Now, the list in Python, kind of like the array list in Java, kind of like the vector in C++, all have mechanisms to extend. So in Python, it's append, right? In an array list, it's insert or add, right? So those structures kind of blend the random access time, quick time access of an array with the flexibility of inserting new elements at the end. But, and so how they achieve that is a bit of magic. I'm calling it magic because I'm not explaining it to you. If you know how it works, do you know how it works? Oh, right. So so it's also magic to you then. Yeah. All right. So it's not magic to me. I don't know how specifically it's implemented. I know of a way to do it so that it appears to be efficient. But what essentially is happening is, if you think about what the challenge with something like that is, the reason why you get a speed with an array, if you pre-allocated the space, you've laid out where all the points, the cells are, right? If each integer needs 4 bytes, and you ask me, give me an array of 100 elements, I just allocate 400 bytes consecutively, and wherever that address starts, that's index 0, and index 1 is going to be 4 more than that, and index 2 is 4 more than that. So if you then ask for index 50, that's going to be address 200. I'm done. I know exactly where to find the things. Now, if you ask me to insert element, what that mean? I already pre-allocate this in memory. Maybe something is right behind it. Ask me to insert would mean I need to grow this array, but grow it to where? I don't have any space adjacent. Might be something already occupying that location in memory. And if I start making it disjointed, now I can't calculate that address so quickly. So what am I going to do? That's the challenge, right? That's where the mystery is on how you do that. Now, all these data structures, fairly modern, the array list in Java, the Python list, that idea of hiding the detail of that magic of, oh, you just grew out of the space you had. Okay, quick, before them notice. Make you allocate some bigger space, copy over everything like nothing happened, and just expand into that space. And that's what you do. Now, as long as you don't do it too often, nobody notices. But that's a different story, okay? What I want to try and do is keep it simple and keep it, I'm not saying naive, but keep it at the level where you can actually see what the implementation is doing at the concrete implementation level. So if you think it's strictly linked list, that's sort of one extreme. If you think strictly array, that's the other extreme. These can be a sort of hybrid, where I could have a linked list of arrays. And so, depending on where I'm trying to access, I might say, oh, it's in this chunk. No, maybe that chunk. And then I access that in random, in order one time. Okay, anyway, that was a little bit of a divergence from going back to what I want to focus on. If you just focus on the simplest of implementations, linked list might be what would come to mind. You could try the array too, but it has a challenge that I just illustrated to you, that you can't really insert it dynamically into your array without having to copy over your elements. All right. So suppose we tried the linked list. I could try something similar to what we did, the discussion we had with the priority queues, right? I could have a linked list of what would each element in my linked list be? A key value pair. Good. So I could have a linked list of pairs, but this time the pairs are not priority element now, they are keys values. So option 1, linked list. And does it matter? Do you think it helps to keep them ordered or not ordered? Ordered? Well, let me put that in the same line. Then in that case, that's the backbone of my linked list, and my elements are pairs, and I'll have my key and my value. And let's say I have n values, n associations. So in the case of order, then we would have, actually, for a dictionary, your keys have to be unique, so no equality. Okay, let's then argue or discuss what the time complexity of each of these operations would be in this context. So once again, I'm going to do, let's see, talking about insert. I guess I didn't mention delete, but certainly delete might be necessary as well. So let's include that. Okay, so here we have our ordered linked list. What would the time complexities be? Worst case now. For insert. Well, how bad could it be? So I have n elements already in my dictionary. I try inserting a new element. Order n, right? It could be that the key I'm trying to put in, well, if I'm trying to insert it, I hope it doesn't exist. Unless I'm reassociating. Where would it go though? Yeah, it's not just about not existing, but if it's bigger at n, bigger than all of them, so therefore it belongs, since I insisted on keeping it in order, if it's bigger than the last one, then I'd have to cutter down this list n times before I found out that it belongs here, and then insert it at the back. So this is at worst, these are all worst case, order n. How about looking up? Order n? Because maybe I have to find, maybe ask for the one that's at the back. Why? Just don't look at that all. How about deleting? Suppose you have to delete the element at the back. For the lookup, it could have even been worse. I mean, you could have even asked for an element that's not in there, a key that's not in there. So, okay, doesn't look like there's anything redeeming about that. Because we got ambitious now, right? Order n used to be good, but now we're looking for log n. We've been spoiled a little bit, right? All right. How about if we were unordered? Sorry? To insert, if it's unordered, just stick it at the front. But to look up and to delete. Okay, so if you're going to use a linked list, what this is saying is you might as well just throw it on in the front and don't bother with any structure at all. Now, take that with a grain of salt, because maybe in the particular application, well, all right, actually, you don't need to take that with a grain of salt, because after you finish this course, you shouldn't be caught dead implementing a dictionary with a linked list, unless you know that the number of elements never passes 3, and then you're good, because it's constant anyway, or some small number. But you shouldn't even be thinking after you finish this course that linked list is even plausible. I'm trying to think hard about any context in which you might think linked list is okay for a dictionary. So anyway, I haven't come up with one yet. If I do, I'll tell you. Right. So the question then is, can we do better? Yeah? Oh yeah? Oh. What? You wouldn't what? I see. Not necessarily. Yes, question? Yeah. Okay, for the keys? Yeah. So, okay, that structure that you're describing is called a trie, T-R-I-E, where each letter. So the suggestion was, what if you store a tree structure that, if let's keep this simple. Suppose the keys are digits, like ID numbers. So everything is between 0 to 9, each digit. And so you could imagine a tree that has, at the very root, 10 children, numbered 0 to 9. And then when you go down, so any ID number that starts with a 0, you go down to 0 link. And then the next digit, again, each node has 10 children. And so, if you have a key in there, like, 0, 1, 2, for example, you'd go down the 0 link, the 1 link, and the 2 link. And then at that node, you'd store the associated value. Okay, and so now if you have the key, you don't really query anything. You're just simply following the path. That structure is called a trie. It's very efficient. Very, very efficient so it's a kind of dictionary as well, because you could, instead of associating it with a value, let's say you're trying to do a spell check dictionary. That's actually one way of doing your spell check real fast. Spell check, you're not really associating the word with a meaning or anything. It's really just to associate whether the word exists or not. So it's like you have a Boolean associated with the word. Right? If you spell it wrong, that's false. If you spell it right, that gets a true. And so that's actually how you would implement. That's a very good way to implement things like spell check dictionaries and sets of elements. But when you have to, and even, okay, if you have to associate it, that could work as well. That takes a lot of space if you're not careful. And you have to know something about your keys to be able to do that. Like ahead of time. You have to know what kind of keys you might work with. Nothing wrong with that. That's not the method I'm going to talk to you about, though. All right. And because I'm basically approaching the end of the time, I'm going to introduce the idea here. So you may have seen this concept of binary search tree in year 1 somewhere. And here's the general gist of what we're trying to achieve. We would love, if it is possible, so here's the idea. So I'm going to put a binary search tree here with a big asterisk on it, because as we explore this, we're going to discover that not any binary search tree is going to fly. But let me transfer the gist of it to you. What if we could arrange our keys in a binary search tree, in such a way that knowing what's at the root and what we're looking for actually tells us whether we must go left or right? Remember, the problem with it searching the heap was after you do that comparison, when you compared 100 with 3, you still don't know, so you know it's not there at the roots, but it tells you nothing about whether you must go left or right. What if we organize this differently so that after that one comparison, you would know whether you should go left or right? Then that would eliminate the trouble of having to search both sides. You'd only have to search one. Okay? So that's going to be the idea of the binary search tree. And how do you do that? You just make sure that the organizing principle of a binary search tree is that every element to the left of a node is going to be less than it, and the elements to the right are greater. Now you can see how that's going to help, right? Because if I say that the root is a 3, and I'm trying to find 100, I know I don't need to go to the left. I need to go to the right. Okay? So that's going to be the idea. And of course, if it works, I'm out of time, so I'll show you the actual binary search tree and write up the definition and so on next class. But if it actually works, what do you think, if everything is beautiful and the tree is looking like this kind of tree, what do you think would be the time complexities of these operations now? Everything? Well, let's think carefully one at a time. If I had to stick an element, maybe you don't know why. Okay. To insert, how would I do it? I'll just search for the key I'm trying to insert. And if I'm going to search, what does that mean? That I might look at the root, not there. It will tell me if I must go left or right. And each node I step to, it will tell me if I should go left or right. So I will know it's not there by the time I get to the leaf and I didn't find it. And all I'm seeing are empties. So I say, oh, so it belongs here, either left or right. How many, relative to the height of the tree, how many steps would I have taken? To the height of the tree, not the number of nodes. I'm saying proportional to the height of the tree, right? Okay, so I'm going to write that as H, not N. So this is going to be theta H. And for lookup, well, that's the same process. And for delete, that one a little bit tricky. You're going to have to see why, but it turns out to be also H, where an H is height of the tree. Sorry for writing so low on the board. Hopefully, camera can zoom in and pick this up. Matthew. Pick that up. All right, and then, so next lecture we'll talk about how that height is related to the number of nodes, and we're going to see where